Okay, this is also from physics. Suppose we got a general surface. Okay, and a force, and extended force applying perpendicular on it. So we define the pressure as a function of every point on the surface. Let's say this one, the general point, let's call it M, for instance. The pressure of M equals to the derivative of the force with respect to area. Means take an infinitesimal area containing M, and the pressure would be the amount of force applying on this over the area of the infinitesimal surface. Okay, this is the definition of pressure. And again, pressure is the derivative of force. So force is an antiderivative of pressure. Now so F would be the integral of P, it is not just for the point M, it is for every point on the surface, the integral of P dA from something to something. Okay, and let's have an example, makes it more clear. Oh, sorry, everything. Pn equals derivative of F with respect to A. This is what was out of the screen. Okay, F, let me say it again. P would be equal to derivative of F with respect to A, so F is an antiderivative of P, so F would be this. Okay, from something to something. Let's have an example on that. We got a container. Full of water. I'm not gonna draw the water inside. So the water got pressure behind this, behind every sides of this container, and we want to find the force applying on this side, on the front side. Okay, and now again from physics we know that the pressure here would be equal to rho GH. Here rho is the density of water, G is the acceleration of gravity, and H is the distance from the water surface, from the top. Okay, here here what in the physics textbooks you see is that they say, okay, pressure is dF over dA, so I write the rest here, so dF over dA, so multiply both sides by dA, that gives us P dA equals dF. Okay, and then integrate both sides, and what is the dF, here you divide the surface into infinitesimal surfaces or parts like this, and the sum of the force applying on each of them would be the whole force, so the integral dF would be the whole force. Let's show it by the little f. Okay, from 0, which means here, which the area is 0, to the whole area. Let's say A of 1, the area of this rectangle. Okay, now let's calculate it. Substitute rho GH here, 0 A1 rho GH dA. But this is dA, this is H. We couldn't calculate it the way it is written like this, but we should write dA with respect to H. How? dA was the area of the infinitesimal surface. Let me draw it here, this infinitesimal surface. And so what is its area? And let's call that 1, take that to be equal to 2, this side, and this side to be equal to 1. It doesn't seem that it is greater than this, but let's suppose that. So the area of this would be, this is 2, would be dA, would be 2 times this. And what is it? This is just this. This is dH. This is H, the distance from the top. So an infinitesimal change of it is dH. So let's just substitute here 2dH and take this 2 here, dH. Okay, and let's And now we should find an antiderivative of 2 rho gh, this, okay? And what about this? Rho gh squared. If you differentiate it, that would be 2 rho gh. Okay, this is simple. From again, this is h, and the limits should be the limits of h. So that would be from 0, which means here, to here, which is 1. This is 1. Okay. So from 0 to 1, which is this, which is rho g 1 squared minus rho g 0. Oh, sorry. No, okay, this is okay. Minus rho g 0 squared. This is 0, this is rho g. So the force would be rho g. Okay.